Okay, we'll continue our discussion on the module 2. So, in the previous sessions, Professor Purushottam as well as Professor Abhilash has discussed about module 2 with the design of impact and design of dynamic loading conditions. We'll continue our discussion with the design of dynamic loading conditions. In the previous session, Professor Abhilash has explained about the endurance limit, the high cycle fatigue, low cycle fatigue, the materials will be under high cycle fatigue and low cycle fatigue, then cyclic loading, these things. So we'll continue our discussion. In today's session, we'll discuss about the factors which affects the endurance limit and the fatigue strength under the fatigue load. Then we'll try to derive a Soderberg equation. So the first one is effects of factors on endurance limit. So endurance limit, already you can calculate endurance limit using the equation half of the ultimate strength, 0.5 into ultimate strength, that is what given in the data handbook. Apart from that one, half of the ultimate strength. So to calculate ultimate strength, okay, in the tension testing machine, we are going to consider a member and you are going to assume that member is smooth and it is perfect in the surface finish, as well as the size we are going to consider as standard specimen to measure or to record the property of the material in the form of ultimate strength. Then we are going to consider for a particular loading condition. So here, if the surface condition is not the perfect surface finish, like for the naked eye, if you see any material, you can feel it is a perfect surface finish or it is smooth and nice, but for microscope, for a microscope of having a higher magnification, in the case of optical microscope or scanning electron microscope, you will find the roughness, you will find the surface roughness on a smoother surface which is smoother in the naked eye. So none of the material you will find as perfect surface finish material. There will be certain roughness on the material. None of the material is smooth. So considering those roughness, microscopic roughness, where it is also called as asperities on the surface. So considering those roughness, microscopic roughness, so C, the surface correction factor coefficient is introduced here. So endurance limit will be multiplied by C, where this C is a surface correction coefficient which will be always less than 1. Less than 1 means it can be 0.5, it can be 0.8, it can be 0.9, it can be 0.95, it can be 0.7, like that. It will be less than 1. So what happens if a number is multiplied with point something, like fraction which is less than 1? Obviously this term is going to decrease. If you multiply 100 with 0.5, you will find 50. The number is going to reduce. So that is what taken care here. So sigma endurance you are going to calculate for a smooth surface finish, assuming a smooth surface finished specimen, but none of the surface will be smooth in the microscopic level. Therefore, to correlate with the roughness, microscopic roughness of the material, you are going to multiply with factor C, surface finish factor, that will be less than 1. So you can correlate with the smooth roughness of the material. Then the second one is size effect. Again, you are going to consider a standard size of the specimen for fatigue as well as for the tensile test. You might have worked on the UTM machine where you have used a standard specimen to calculate, to test the specimen under UTM. Okay, here consider the standard specimen. If the size of the specimen is different, if it is not of the standard, then you need to again correlate with the different size apart from the standard specimen. So to correlate with the different various sizes, this size quotient is introduced, where again you are going to multiply endurance limit with the size factor. Again B will be less than 1. If you multiply any number with a number less than 1, this will be reduced. Okay? So you are going to reduce the capacity of the material to be in the safer side. If you want to calculate the diameter, and if you calculate the diameter considering the less capacity, you will be having the diameter more recommended diameter or more safer diameter. Okay? So to design for the safer condition, we are going to consider the capacity as less by considering these factors. Okay, where this is about the standard size and various sizes. Similarly, effect of load on endurance limit. Again, the endurance limit, the fatigue strength calculation, there is a machine, something like UTM, to calculate the fatigue strength of a material. Again, there is a standard specimen size. So you are going to prepare a standard specimen size and you are going to load it on the fatigue testing machine, and you are going to test it for one loading condition. Okay? Only one loading condition. If the loading condition is different, say for example if it is bending, or if it is cyclic bending or reversed bending, or cyclic axial load or reversed axial load, like that, if it is varying, then again you need to correlate with the various loading condition. In the laboratory we are going to test it for only one loading condition. If it is varying loading condition, again we need to correlate with that load. So the effect of loading on the endurance limit is A, multiply endurance limit with A, where again A is the load correction factor, load correction coefficient, which is almost equal to 1 or it can be less than 1. Okay, for a specimen which is not of the same kind of loading as of the test condition. Similarly, the effect of reliability, if the reliability of the material is less, again you need to multiply with the factor, reliability factor, to be in the safer side. Similarly, if there is a stress concentration means if there is a discontinuity in the material like notch, or maybe like a groove, or maybe a stepped shaft. Okay, if there is any discontinuities, then obviously stress concentration comes into picture because there will be change in the area. Okay, if there is a groove, then area will going to change at that particular point. If the area is decreased, then stress obviously is going to increase. If there is a stepped shaft, I will take for an example like this. This is a stepped shaft. Obviously at the section 1-1 the area will be more, and at section 2-2 the area will be less. Obviously at this particular point where the diameter is decreasing, the stress will be more. So the stress will be concentrated more on this particular position. Similarly, if there is a notch, like this, okay, at this section and at this section you can feel the difference in the area. At section 1-1 the area will be more, and at section 2-2 the area will be less. So the stress will be concentrated more on this particular area. Okay, so this is what the stress concentration effect. You need to correlate with the stress concentration effect, where you need to find out the stress concentration effect with the charts available in the data handbook, where the stress concentration effect will be always greater than 1. It will be at the range of 2, 2.5, 2.3. Therefore, it is divided by 1 divided by KTF. So 1 divided by any number greater than 1 gives you the number less than 1. Okay, again multiply with this one, you will get endurance limit, reduce the endurance limit. So considering all the above these factors which affects the endurance limit apart from the testing condition. So testing condition we are going to assume certain surface finish, we are going to assume certain loading condition, we are going to assume certain standard dimension, okay, and we are going to assume certain reliability. Reliability we are assumed as 50% usually. Therefore, we are going to consider sigma endurance is equal to 0.5 times sigma ultimate stress. So this represents 50% reliability. If it is greater or lesser, you need to multiply those factor respectively, correspondingly. Okay. So considering these aspects, So this is the surface condition which is microscopic level, but this stress concentration is macroscopic. You can feel this with the naked eye, but you cannot feel this with the naked eye. This is microscopic and this is macroscopic. So considering all the 5 factors, the endurance limit can be written as endurance limit multiplied by A, B, C divided by KTF. So this you can find it in the equation, the reference for this in the equation 2.21 CDE in the page number 25. You can open your data handbook, you can go to page number 25. If you observe the equation, you will find this one. Endurance will be multiplied with ABC and it will be divided with KTF. So this is the factors which affects the endurance limit. Okay, so the next topic is fatigue strength under fluctuating loads. So if any member, if it is subjected to fatigue loading condition, then the stress will be varying with respect to the time, because fatigue means load as the load varies with respect to time. Obviously the stress will be varying with respect to the time. So if the stress varies with respect to time, then you will find the amplitude of the stresses, because stress means there will be certain magnitude and time means you will find the cycle. Okay, since there is a cycle, you will find some amplitudes. Therefore you will find the amplitude stress whenever a member is subjected to cyclic load or fatigue load. Then since if there is amplitude, then obviously there will be mean stress. If you consider the mean of the amplitude, there will be mean stress. So here mean stress and amplitude stress is considered for the discussion, because the mean amplitude stress and the mean stress are the effects of the fatigue loading condition. If a member is subjected to fatigue loading condition, you will find amplitude stress and the mean stress. So here amplitude stress and mean stress is considered. So amplitude stress is taken in the y-axis and the mean stress is taken in the x-axis. Now if a member is subjected to loading condition, certainly at some point of time it is going to break or it is going to fail. So I will consider some failure points. Okay, I will start with 0. If the amplitude stress is 0, then what will happen? Amplitude stress 0 means no amplitude. No amplitude means the type of loading will be static. If the type of loading is static, then the criteria of failure in the static loading condition will be yield stress and the ultimate stress. So if the amplitude stress is 0, then this line, the x-axis line, represents the amplitude stress 0. So this line represents the static loading condition. The member is subjected to static loading condition. So the member is going to fail with the yield stress or the ultimate stress. That I will take it here. This point, yield stress sigma ys, and this point I will take it as sigma ultimate, because sigma ultimate stress will be always greater than the yield stress. So along x-axis, since the amplitude stress is 0, amplitude stress 0 means no amplitude. No amplitude means no change in the stress with respect to the time. That means to say it is static. When the member is loaded to the static loading condition, the criteria of failure will be yield stress and the ultimate stress. That is what I plotted here. Similarly, when the mean stress is 0, when you find the mean stress 0, when it is completely reversed, when the load is completely reversed like this, positive and negative, or tension and compression, continuous tension and compression, continuous bending to and fro like this. Okay, whenever the completely reversed load takes place, mean stress will be 0. That means it will be the reference point. So when mean stress is 0, this is the line which represents mean stress 0. So from this point to this point, mean stress will be 0. I am not considering any mean stress. So if the mean stress is 0, then the type of loading will be completely reversed loading. Out of 3 fluctuating load, it will be completely reversed loading. that means the worst case of fatigue loading. So if it is completely reversed, then the criteria of failure will be endurance limit. Therefore, I am going to consider anywhere on this line sigma En. So on y-axis the mean stress is 0. Mean stress 0 means it is completely reversed loading condition. Whenever a member is subjected to completely reversed loading condition, the failure criteria will be endurance limit. On the x-axis, the amplitude stress is 0. Since the amplitude stress is 0, no amplitude means no change in the stress with respect to the time. That means it is static. So for a static loading condition, sigma ys and sigma ultimate end stress and ultimate stress is considered as the failure criteria. Okay. So from this to this, from mean stress 0 to ultimate amplitude stress 0, if I consider some of the failure points here, like this for different loading conditions, the failure points will be something like this. Okay, so these are all the failure points. These are all the failure points. Now the thing is, we need to join endurance with yield stress, endurance with ultimate stress. How you are going to join it? So there are three researchers or three scientists who worked on this, where the first person, whose name is Gerber, used to join with the smooth curve like this, with the smooth curve from endurance to the ultimate stress, something like this. He used some parabola pattern to join endurance and ultimate stress. Okay, this is Gerber parabola. This is called as Gerber parabola. Then one more scientist used to join endurance limit and ultimate stress with the straight line, something like this. This line is called as, I'll use different color. So this line is called as Goodman line. Then again, one more fellow, he joined the endurance limit with yield stress, something like this, and this line is called as Soderberg line. Okay, so these lines indicates the points within the parabola is safe, and the points which is beyond the parabola is failure. Similarly, this line suggests the points within the line is safe and above the line is failure points, and this line indicates the points within is safe region. So these regions are called as safe regions, and these regions are called as failure points or failure region. So this is what the fatigue strength analysis using fluctuating loads with three different approaches, joining endurance limit to ultimate and endurance limit to yield stress. Okay, the Soderberg derivation, next topic. It is very important derivation. So again here the graph is considered like this: amplitude stress versus the mean stress, because whenever a member is subjected to fatigue, then you will find amplitude stress, because the load will be changing with respect to the time, therefore stress also will be changing with respect to the time. So whenever load as well as stress changes with respect to time, you will find the cycles. Whenever you find the cycles, there will be amplitude, therefore you will find amplitude stress, that is the cause, and since there is an amplitude, there will be mean. So mean stress I consider in the x-axis. Similarly, as explained in the previous session, if the mean stress is 0, then the criteria will be completely reversed. Look at here, if the mean stress is 0, then the type of loading is completely reversed. So in the completely reversed cycle, you will find mean stress is equal to 0. In the reversed cycle or fluctuating one, you will find mean stress is equal to some number, but in completely reversed, that is the worst condition of the fluctuating load, you will find mean stress is equal to 0, where the load will be changing in its magnitude, positive to negative. Okay? If the mean stress is 0, then the criteria of failure will be endurance limit. Similarly, when the amplitude stress is 0, the type of load is static, because if there is no amplitude, means to say it is not changing with respect to the time. Therefore, if the stress not changing with respect to time, amplitude stress is 0, the type of load will be static. For static loading condition, the criteria of failure we are going to consider it as yield stress or ultimate stress. That is what I have plotted here. Now, I am going to use the Soderberg line. So, Soderberg has joined these two failure lines by a straight line, where few of the failure points will be there, something like this, failure points. So, he suggests that the points well within the line will be safe, and the points outside this will be a failure points. Okay. Also, you can use the factor of safety. If you use factor of safety, this will be sigma n by n. N is the factor of safety. Similarly here, sigma ys by n, where n is the factor of safety. You can use factor of safety here itself, or you can introduce factor of safety later. Okay. So start with this one. If the amplitude stress is 0, type of loading is static, then the failure criteria is yield stress. If the mean stress is 0, type of load is completely reversed, failure criteria will be endurance limit. Therefore, since this is the straight line, I am going to consider straight line equation which you have studied in your PUC, okay, 12th standard. So, considering the straight line equation, x by a plus y by b is equal to 1. This is the straight line equation. So, in x, we are going to consider it as mean stress. So, substitute in the place of x mean stress. A, the intercept of the x-axis is yield stress, sigma ys, substitute at the place of a, sigma ys, plus y-axis. In the y-axis, we have considered amplitude stress. So, y replaced with sigma a. Then b, on the y-axis, we mark endurance limit here. So, b mark endurance limit. Therefore, mean stress by yield stress plus amplitude stress by endurance limit is equal to 1 is the Soderberg equation. So, if we consider the factor of safety and other factors which influence the endurance limit, like size correction factor, surface correction factor, load correction factor, like that, then this equation can be modified and written as like this: mean stress by yield stress plus amplitude stress into KTF divided by sigma endurance into ABC. Or you can take KTF in the denominator, sigma endurance into ABC divided by KTF, which we have discussed just previous to this session, is equal to 1 divided by n, where n is the factor of safety. So, this equation you can find it in the data handbook, page number 25, equation number 2.21c. You can find this equation as Soderberg equation to solve the problem. Remember, subjected to cyclic loading condition in one direction, like cyclic loading condition axially, cyclic loading condition in bending, or cyclic loading condition torsion. So, simple cyclic loading condition, whenever a member is subjected to simple cyclic loading condition, you are going to use this formula to calculate the unknowns. Whenever a member is subjected to compound cyclic loading, like cyclic axially, cyclic along bending, cyclic axially, again cyclic in torsion, combination of axial cyclic load and torsional cyclic load, combination of bending cyclic load and torsional cyclic load, combination of axial cyclic load and bending cyclic load. You are going to use, whenever a member is subjected to combined loading, you need to use the principal stress equation, the same thing will be continued here but in different fashion. So you are going to use the same equation in different fashion, again you will be end up with the principal stress equation. Okay. So in the next session we will be starting with the problems where we will be dealing with initially we will be dealing with the member subjected to simple loading, simple fatigue loading condition in any one axis. Then we will be moving on to solve problems with combined cyclic loading conditions, member subjected to combined cyclic loading conditions.